Today I am only going to be reviewing over the material for the exam. So it's just 3 chapters, but it's a lot of content. So let's look at the 3 chapters. So first one here is chapter 25, geometrical optics. So this is where we introduce light behaving as a ray. That is, it has a starting point, just goes in a straight line unless it hits something, in which case it becomes a line segment. So that's the idea of the ray model. We learned Huygens principle. Make sure that you understand what Huygens principle is. Just look extra hard. Sorry, I'm used to with your class. I don't have to worry about that. Okay, well, come on. Huygens principle is the idea that when you have a wave traveling, each point on the wave can be treated as a point source for a new wave. Also here we have the idea of wave front. So make sure you have the idea of the wave front being the place where you have essentially one way of thinking of it is all the peaks of the wave as you look through space. So remember we had a picture of a pond that had ripples going out, and the peaks of those ripples, so the water's going out in a radial pattern, and the peaks of the ripples are the wave fronts. So make sure you have that idea clear in your head. It's kind of important for the analysis using Huygens principle. Then we had the laws of reflection and refraction. We had 2 kinds of reflection that we talked about. There is a third type. It's called phase conjugate reflection. I didn't talk about it. Clearly, you don't have to know it. It's very rare that a physics textbook would ever talk about it. So what are the 2 types of reflection that we did talk about? One starts with S and one starts with D. Here are words that are not the correct ones that will lead you in the right direction. Spectacular and difficult. Specular and diffuse. Specular reflection is reflection that is mirror-like. And so specular reflection, using Huygens principle, it's very easy to show geometrically that you're going to have the angle of incidence equal to the angle of reflection. Specular reflection, mirror-like, you have to have a flat surface. Diffuse reflection is reflection off of a rough surface, such as the example of my forehead. My forehead is rough. And because it's rough, if you look at the reflection, instead of seeing a nice reflection of your face in my forehead, it's just kind of dull. And when you do see a little bit of bright reflection off my forehead, it's simply because I have a layer of moisture that is smoothing over the roughness of my forehead. And you get about 5% reflection off of that moist layer. Now, when you're using the law of reflections says theta incident equals theta reflected. We use the same method for measuring the angles in all of our interactions with the surface. So how do we define the angle of incidence? The angle between what and what? Between the surface normal and, well, incidence is the incident ray. The theta reflected is between the surface normal and the reflected ray. For reflections, that's not super important, but for refraction, it's ultimately important. And so we use the same rule for both. Total internal reflection. Total internal reflection comes after we've studied refraction. So we have to go to refraction before we can get to total internal reflection. Refraction is light bending when it goes from one material into another. You'll be given Snell's law. but you also need to do basic interpretations. Like, if I have light going through unknown medium 1 and then goes into unknown medium 2, if the light has a path like, so here's the interface, here's medium 1, and here's medium 2. If the light goes, well, that's the wrong color, right? If the light goes like that, what does that tell you about the media? It tells you one basic thing. Okay, I was looking for something more specific on that topic. What does it specifically tell you about the indices of refraction? What? No, this is just one. Erika? Well, which one is slower then? Are you saying 2 is slower or 1 is slower?
2 is slower because 1 to the y-axis.
Other way around. When you go into something slower, it refracts toward the normal. When you go into something faster, it refracts away from the normal. So the fact that this angle of refraction is bigger than this angle of incidence means that it's faster over here and slower over here. Index of refraction is n is equal to c over v. So faster means n is lower. So N1 is greater than N2 because it's slower in medium 1 than in medium 2. So this is the one specific thing. Okay, those are 2 equivalent statements. So that's why it's one specific thing, is what you can tell directly by looking at that diagram. Now, if you know what the angles are, if you know what theta incident and theta refraction is, then you could also find the ratio, because you could use Snell's law that says so we use Snell's law to actually find the ratio of those 2 indices of refraction if we know the angles. I still can't tell you what the index of refraction of either of them are, but I can tell you that much. What would differ if I changed the arrow directions on these? If I changed it to go like that, should the second line change or stay the same? It stays the same because light works the same forward and backward. Now I'm going to change these arrows back just because of my words incident and reflection on the diagram, and I don't want those words to be wrong in the future. So that's Snell's law. It tells us that when you go into a faster medium, the light will refract away from normal. When you go into a slower medium, it's going to refract toward the normal. That leads to the possibility of, if you have a big angle of incidence. So actually, let's go back to my picture here. If this angle of incidence is a big angle, then you could get to the point where the refracted ray would have an angle of refraction of 90 degrees. Angle of refraction of 90 degrees is the maximum possible angle for refraction. Why? Well, the maximum value that sine theta can give you is 1 that occurs at 90 degrees. If you were to have an angle of incidence bigger than what I have with orange, it would require sine theta 2 to be bigger than 1. But sine can never be bigger than 1. Sine just goes between -1 and +1. So Snell's law breaks down if you have the angle of incidence is too big. Now, the angle of incidence is freely controllable And so you're like, how can I make Snell's law break when I can freely control it? Well, what happens if your angle is bigger than that angle of incidence is bigger than the angle that would result in a 90-degree angle of refraction?
Could it be that you can let's just say it goes to the other side and it's like over 90 degrees? Couldn't you like take away 90 and count it as a negative?
Well, no, because the equation that gave you the 90 no longer works.
Well, like I mean, like since it's a different quadrant, like just do it negative then. Nope.
At that point, it simply stops refracting. There is no such thing as refraction at that point because the equation is broken. Instead, it reflects. So if you come with an angle that's bigger than that, so if you come in like this, then that's supposed to be a straight line. So if you come in an angle like that, it's going to reflect. And so then we're just going to have our angle of incidence is equal to angle of reflection. So we call that total internal reflection when your angle of incidence is bigger than the maximum angle that can occur, that can have refraction occur. And so that's this total internal reflection idea right there. It occurs when you have an angle bigger than the angle that would require 90 degrees for the refracted light. So you can always find the critical angle just by saying n1 sine theta 1 equals n2 sine of 90 degrees. And that instead of 1, I'll put theta critical. That's not a C either. That's how we define the critical angle. We just put in 90 degrees for the refracted angle and theta critical for the incident angle. Now notice you can only have total internal reflection if you're going from a slower into a faster medium. If you're going from a faster into a slower medium, it always refracts toward the normal. That's never going to be a problem. It's only when it's refracting away from normal that you have that problem. Okay, be able to identify the geometry of a rainbow. Rainbows, we have droplets in air. For the first order bow, light comes in, different colors are separated because of dispersion. Dispersion is that you have a different speed of light for different colors. So because you have different speed of light, you have a different index refraction, thus you have a different refraction angle. So the light is spread out. You have one reflection, comes like this. I always draw these. I wish I could rotate with this, but I can't. I always draw these so you're looking down at the rainbow. I don't know why I choose my angles that way. But you have the light coming at you at different angles. And so you got the sun there. The angle from the sun to the light droplet to you is between roughly 40 and 42 degrees for that first order rainbow. And so geometry dictates that, if the sun's at that fixed point, this angle here is going to be the bottom, this angle here is going to be the top. That's where I see my rainbow. And of course, that angle is going to be symmetrical around the line that goes from the sun through my head, which is why you get circular rainbows. Because you're simply looking at light following that arc. So the angular size of a rainbow is always the same. If it's closer, it's going to be smaller because it's, with respect to everything else, you can tell it's smaller separation. Second order bow, so that was the first order bow. What's the difference between the first order bow and the second order bow? Okay, it's inverted. You start with the light coming in the bottom. The bigger difference is bigger difference is I can't draw. you have 2 reflections instead of 1. And because of those 2 reflections, you have 2 crossing points. There's 1 crossover. There's the second crossover. That one only had 1 crossover. So the rays, the colors cross over each other twice, giving you a reinversion of the order of the colors. So the order of the rainbow colors is reversed because of the second reflection. So second order rainbow has 2 reflections. First order rainbow has 1. On reflection, approximately what percent of the light is going to be reflected? These are not hitting beyond the critical angle, so it's not 100%. So approximately what percent is reflected? Okay. He said around 8. Oh, 80? Oh, no. 8 would have been much better. The way to actually calculate, you do not know how to have to know how to calculate it, is that it's the reflection is 1 plus n over 1 minus n quantity squared. So for water, that's about 2.33 over, well, minus 0.33, but who cares when you're squaring? Actually, no, I did that backward. So it'd be 0.33 over 2.33 squared. Let's just calculate real quick to see. That squared is 2%. So for water, it's only about 2% of the light that's getting reflected. So you're not seeing bright light from the rainbow. If it was, 80%, you would have really bright rainbows. Anyway.
Why is the top number negative?
Because n is 1.33, so 1 minus 1.33 is negative 0.33. It doesn't matter because we're squaring it.
Okay. I was just wondering, and then the bottom is 2?
Well, 1 plus 1.33 is 2.33. I did right what? So I put in 1.33 for n in both cases. Right? You don't have to know how to calculate that reflection percentage. But it's only about 2% that you get reflected. For the second order bow, it's 2% of 2%. That's a pretty weak second order rainbow, which is why you usually don't see them. Then we have probably the hardest thing for you to do in this chapter. That is the ray tracing and using the Thin-Lens equation. So ray tracing, I did, 3 examples in class of different forms of ray tracing. I'll do one more here today. I showed you where you could look on YouTube to see me doing more examples of ray tracing. You are going to have to use a ruler. You don't have to have a protractor this time, just a ruler, to draw an accurate ray tracing diagram to solve a problem. You could use the Thin-Lens equation to confirm your answer, but I'm going to be looking to make sure that your ray tracing drawing is done right. It's not looking for the right answer. It's looking to make sure you can do the ray tracing. So let's just do an example for ray tracing. Just going sideways on here, so it's all this topic on the slide going out to the right. Give me an example you'd like to see. That is a lens or a mirror, a converging or diverging, an object closer than or farther from the focal point. So let's just start off lens or mirror. Somebody blurt out. Okay, mirror. And do we want it converging or diverging? And do we want the object, in this case it doesn't matter, I'll tell you, closer or farther than the focal length? The truth is it's always farther than the important focal length if it's a diverging lens or mirror, because the focal points are on the opposite side. So we would have to be on the wrong side to have it the other case. So it's always farther than. So now we can do this. First thing I need to do is make my optical axis, or principal axis as we call it. It's a principal axis like the principal item, not like the dude who's in charge of the school. And then I'm going to draw my mirror. If it's a diverging mirror, I'll put the object actually first. Here's my object. We always put the object on the left just by convention. If you put it on the right in the test, I'm not going to mark you wrong for that. But by convention, we put it on the left. It just keeps things easy for us. For the mirror, I'm going to make the mirror as a straight line. I didn't try this. Try it again, see if, all right, because I'm not on top of the PDF, it actually is working. Well, then I'm going to remake my principal axis to make it actually a straight line. Can you guys even see my ruler? So there's principal axis. Now I'm going to put my mirror here, and for my mirror, I just put a vertical line. My mirror is really curved, right? But we said that we're going to use paraxial rays. Paraxial means parallel to the principal axis and pretty close to it. So the amount of curvature that we actually are going to see with the paraxial rays is small enough, we just treat it as a vertical line. But I do want to make clear that this is a diverging mirror. What way should a diverging mirror bend? Yes. I have to look back here because in my picture, you're pointing the wrong way, but the way you're looking at, you're pointing the right way. So I just draw the edges like the ends like that, so I know, yes, that's the direction of the actual curvature. Now we have 3 rays, and once again, let's list them before we do them. What are the 3 rays we're going to draw? Parallel. Okay, if I could. Parallel. Cool. I could also do the center. I can only do the center on a mirror. So if it's a lens, don't try to do the center ray. If it is a mirror, sure, you can do it. There's one more thing I need, and that's the focal point. Where's the focal point for a diverging mirror? This time I was quicker. Brandon is giving me the signals, and he's correct. Here's the focal point. If that's the focal point, and let me actually be somewhat accurate here. So that's 1, 2, 3, 4.5. 1, 2. One, two, three. So that's the center of my mirror. The radius of curvature is always, well, the focal point is 1/2 the radius. Is what I meant to do. The focal length is 1/2 the radius. So the distance to F, which is called the focal distance, is 1/2 the radius. So the distance to C is twice that. So I've got the center there in case we wanted to. I'm going to do the center ray, so I have to have the center there to do it. So now we'll do the rays, and I will start with the parallel ray. So I'm going to make the parallel ray in orange. There's my parallel ray. Poor choice of color. You can't distinguish it from mirror. How is that going to reflect? Okay? It should reflect so it goes through the focal point. So it should reflect. So it goes to there, right? Now I'm going to draw a dashed line here because the light doesn't go through the mirror. Instead, it reflects. And so there's the light I'm getting for the parallel ray. So there the parallel ray is drawn correctly. Next ray we have is the focal ray, where the focal ray should go from the tip of my object through the focal point. Since the focal point's on the other side, I just draw my line to that point. Man, I've really restricted my color gamut here with the other things I did. Of course, it doesn't go through, so I dash it out. How does the parallel ray or the focal ray reflect? Comes out parallel. It sounds like people are prepared for this one. That is great. Now, you can see immediately this green line is never going to cross the blue line. What does that mean? It's a virtual image. So what do I do to find where the virtual image is going to be? I have to extrapolate back. Now we can already see where the image should be formed, but we always do a third ray to make sure that we didn't just do something errant. So my third ray here is the vertex ray. The vertex ray is going to go from the tip of the object through the vertex. This will be my best attempt at it. So the vertex ray goes like this. And then that's 15 degrees. It's going to reflect. Angle of incidence is angle of reflection, so 15 degrees down. Well, once again, that's not going to meet, so I extrapolate back. Now we have three rays, and because I did it with rulers, it's better than anything I've done in class before because it's always wildly wrong without a ruler. We can see those three are all crossing at almost exactly the same point. But there's one more ray that I could have done, and since I'm trying to illustrate how this thing works, I am going to, I should have named these. This is the V ray. Whoops. That was the F ray. This is the V ray. So the last one would be the center ray. So the center ray should go from the tip of my object through the center of curvature. And as you can see, this won't give me fractional angles. And it's going to be impossible for me to get the right angle here because that's 6 degrees, which is too flat. And that's 7 degrees, which is clearly too steep. So I won't be able to draw that ray accurately, but that ray should go from the tip of my object through the center of curvature. And you can see that if I was halfway between these, it would cross the same place. Final thing is, where's my image? Let's get this back to 90 degrees because the image is simply going to go from the optical axis to where they all meet. And thus, there's my image. Yeah.
I was just wondering, so to be able to find focal point and focal length, that equation works for all like diverging and converging.
The equation you're talking about is 1 over F equals 1 over distance object plus 1 over distance image, right?
No, I was talking about F equals R over 2.
F equals R over 2 is only for mirrors. For lenses, it's a more complicated. It's called the lens maker's equation.
That's how you were able to set the focal point.
For a mirror only, yes.
Correct me if I'm wrong, why do we have two extrapolations for the focal ray?
One of them is an extrapolation of the incident of the ray coming in, and one is an extrapolation of the reflected of the ray going out. Okay, I'll erase the one that we don't need. We don't need this one. But I needed it to make sure that I had the other one correct. So I drew it, because if I don't draw it, I'm not going to get the other one correct. Now, using my ruler, actually, I could have stopped because my ruler was going the right place. But that's why. There is no light that follows the one that I erased. And there's no extrapolation that's important to us of it. The dash, of course, there's no light on any of the dashed. A couple more things just to make sure that we did this right. This here is the distance object. And this here is the distance image. We have the height of the object. We have the height of the image. We have the thin lens equation, actually. And then we have our magnification equation. This is called the transverse magnification, so I'm going to put M sub t. Which through geometry gives us that simple relation. So those are the two common equations that you would use if you're doing it mathematically. So you're also going to have to be able to use these two equations in the box. But you're going to have one problem that will only be drawing the figure, which is why I spent the time here to do the figure again to remind you how it works. Yes, Erika.
So, you know how you had the focal point and then they were like the first to start to meet the focal point, but then they didn't? Why? Sorry. It's the first, you know how it was the first green line
Okay.
that you drew?
Yes.
You went all the way to the focal point.
Yes.
And then now you said that it didn't really matter.
Well, it mattered for me to get the right angle because that green line is defined as the line that goes from the tip of my object through the focal point. And so I drew those dashes to show, yep, I'm going through the focal point. But the light itself doesn't actually go through the mirror. The light itself reflects, so the solid green is the only light that really existed. And then I extrapolate, because the eye is going to see the reflected light and extrapolate it back. Then I drew this extrapolation that's still showing of what the eye is going to perceive. So the one I erased is not what the eye perceives. I left the dashes for what the eye perceives.
And the black line, that one.
The black line is the vertex ray. So it went to the vertex, reflected down here, and then the eye once again extrapolates it back. Lauren.
Focal length be on a converging mirror?
It's the same equation. A converging is going to be a positive focal length. A diverging is a negative focal length. So for a converging, it's going to be on the front side instead of on the rear side. All right, chapter 26, vision. Now we didn't talk about cameras, so it's just vision for chapter 26. So we have the pieces of the eye, the cornea, the iris, the lens, the retina. Know what each one does that's important for our vision. So very quickly, let's just say, what is the most important thing about the cornea for our vision? Most of our focusing happens there. The cornea is our primary focusing device. It's the thing that should take an object infinitely far away and make it come to a focus on what's the thing that is taking the picture, the thing that's recording the light. What is the thing that takes the picture, the thing that records the light to send to our brain? The optic nerve transmits it from this thing, the retina. The retina is the thing that takes the picture. And so the cornea should be focusing light from infinite object onto the retina if you have normal vision. And normal vision just means what we expect ideal behavior to be. The iris. What's the purpose of the iris? It adjusts to allow more or less light in. We talked about the brain's interconnection there. For the purposes of physics class, the brain's interconnection isn't important, but many of you are looking at careers in the medical field. That's kind of an important aspect of it. So the brain adjusts the size of the iris based on the light conditions. And somebody asked about why do you see better when you squint? Same reason you see better in bright light conditions, because you make a smaller hole, and geometrically you have things that are far apart won't have their light come to the same part in the retina. So by definition, you can resolve those things just based on the size of the hole. The smaller the hole, the closer together the things you can resolve. Hence, you have better resolution even if you didn't have a lens with a smaller opening. So squinting, smaller opening, better resolution because of the pinhole aspect. Nobody's doing pinhole camera for their project, right? Nope. Okay. Okay, what's the point of the lens? If we said the cornea's point is to focus light, what does the lens do? The what?
It's just focusing because it flattens out and it contracts.
Okay, the lens deforms to allow us to change the focus. So it allows us to adjust from focusing on something really far to something closer. And then the retina contains two types of light sensors, things that are shaped kind of like this and things that are shaped kind of like this. And so we call them, conveniently enough, rods and cones. And rods give us light dark. No color. Cones give us color. We have three different types of cones. One that we call the red cone, one that we call the green cone, and one that we call the blue cone. Hence, our vision is in three colors that we call red, green, and blue. Now, being practical, the blue cone has its most sensitive detection in blue, but it detects over a fairly broad range. The green cone has its most sensitive detection actually somewhere in the orange range. And the red cone has its most sensitive region in the red range. The reason we call the green cone instead of orange cone is because it's the primary detecting for green color. And so it's based on those three cones that we have our color vision. And your brain is just saying how much red, how much green, how much blue to give you a color. And we have about 100 steps for each, so we can see a color gamut of about 1,000,000 colors, 100 times 100 times 100. And we talked about some people, all of them women, have a fourth kind of cone, which gives them about 100 times more colors, which is 100 million colors, which is pretty awesome. I don't know if it gives you an advantage in normal life, but it would give you an advantage as an interior decorator. So if evolutionary pressures are going to affect the gene frequencies, people died because they couldn't get the right colors for the rooms, then we would see that trait becoming more and more dominant. And of course, to be clear for people in the origins class, if people were going to die before they had offspring because they couldn't differentiate the colors, then that would be an evolutionary pressure. If you have lots of offspring and then you die at 40 instead of dying at 80, that's not really evolutionary pressure. Assuming you have your kids before 40. Okay, let's not worry about the pigments. I don't remember talking about the pigments. We had lab where we talked about presbyopia, hyperopia, myopia, and astigmatism. So make sure that you are clear on what those four things are and how we correct them, and that you can calculate the correction for just the two of hyperopia and myopia. So we're not going to I'm not going to give you a presbyopia problem. I'm not going to give you an astigmatism problem. But you surely will have something that deals with a vision problem and how we correct it. So as you won't have to do a calculation for presbyopia or astigmatism, you still might have to explain that. Chapter 26, optical instruments. Oh, this is continuation. Okay, so chapter 26 had two pieces. You need to be able to calculate the magnification of a simple magnifier, microscope, or telescope, and to be able to work through the derivations for how we got those. Remember, the telescope was super easy, and I blanked on it in class. Hopefully that helps you remember. The telescope one, you just had the simple angle coming in, light focuses at the focal point of the objective, angle to the eye, light is at the focal point of the eyepiece, ratio of those two angles gives you the magnification. The simple magnifier, that was, again, a reasonably simple geometry. You should know the difference in accommodated versus unaccommodated viewing and why we use unaccommodated viewing for most of our calculations and devices, because it's less eye strain. And then relate to a microscope with that. Distinction between angular magnification and transverse magnification. Transverse magnification was ratio of height of the image to height of the object. Angular magnification is ratio of the angle seen through the instrument to what the angle would be without the instrument. So their angular magnification is something that's specific to our vision and how the angles are bigger or smaller, whereas the transverse magnification is about the image, the ratio of the height of the image to the height of the object. Finally, chapter 27. For each of the following, be able to explain why it is exclusively a wave phenomenon. That is, these things that are listed here are all things that can only occur if light is a wave. And so we have, now I have single slit diffraction, but then I crossed it out. Double slit diffraction, diffraction grating, thin films, and polarization. Let's start with all of them except for polarization have one thing in common. They're all using interference. They're all using two waves meeting together and adding up. Getting constructive interference, destructive interference. So make sure that you have in your head the conditions for constructive and destructive interference. Of course, you'll have the equation, but you need to understand what constructive interference means, what destructive interference means. Then you have, for diffraction, light's bending around a surface as predicted by Huygens' principle, and so you have different path lengths. So you need to take into account the path length variation and the phase conditions for constructive and destructive interference. For the what's the difference in double slit and diffraction grating? There's only one fundamental descriptive difference.
Could you read that 600?
Yeah, it's the number of slits. The ones you use had 600 slits per millimeter. 600 slits per millimeter, that thing's like 2 centimeters across, so multiply that by 20. You know, that's a whole lot of slits that was on that thing. And so you have the light, if it's a 1 millimeter laser beam, it's going through around 600 slits. And each pair of slits is giving you a diffraction peak, but they're all going to be at the same angle for maximum. And if you go anywhere off of the maximum, they're going to have different phases. And because of the different phases, it's going to average out to 0. Because some will be 5 degrees out, some will be 10, some 20, some 30, some 40, etc. If you add them all together, you're going to have as much up as you have down necessary. So the multi-slit, the diffraction grating, gives you just the peaks, and it's destructive everywhere else. Whereas if you have 2 slits, you're going to have place where it's constructive and place where it's destructive, and then everything in between. So for an experimental purpose, we always use a grating, so we have just the peaks and don't have to worry about everywhere else. Thin film interference, remember I told you there's 8 scenarios. There are only 2 answers. you're going to have a problem where you're going to be given a scenario and say, show that this is the equation for constructive or destructive interference. You're going to have to go through and show how the interference equation works out for the thin film. So all of these have in common interference, which is a property of waves. Polarization is a property specific to transverse waves because it has to do with the orientation of the displacement of a wave. So for our electromagnetic waves, they're transverse electric fields and magnetic fields. And with the polarizer by default, we talked about the electric field. And so if we put light through a polarizer, it will only allow electric field oscillation in one direction. So you have light with electric field in all directions, goes through the polarizer, now the electric field is only in the vertical plane, let's say. Now, I think it was Alex pointed out in the lab, remember, the data wasn't ideal for the polarizers. Alex figured out it's because the lights are so bright. If we dim the lights, then you will see much closer to ideal behavior for those polarizers. Something for me to keep in mind for the coming years. Because in the past, I've always just said these are pretty crummy polarizers. You have to look at the general form. That's why I said you got to take a lot of data points. So you look at the general form. Anyway, so polarizers, if you have light that's initially unpolarized, and then you say, I'm only going to allow the amount in the vertical direction through, there are two ways you might view that. One is, well, the amount of light that's perfectly vertical is essentially zero, right? Because it's all going to be like 0.001 degrees off, 0.003 degrees off, something like that. And you might say, oh, well, I expect nothing to go through because there'll be nothing that's exactly vertical. Or you might say, well, the polarizer is not exact, it's plus or minus 3 degrees, and so I calculate how much is plus or minus 3 degrees. It depends on the quality of my polarizer. But that's the wrong way of viewing it. That's, in other words, incorrect. If we have light that has its displacement in this direction, we can simply say, well, the angle between that and vertical we'll call theta, and the vertical component of this is the electric field in this direction times cosine of theta. The horizontal component is the magnitude of displacement times sine theta. And we're only allowing through the vertical component, so I'm only allowing through the electric field times cosine theta. Intensity is proportional to electric field squared, so the intensity that's allowed through is the initial intensity times cosine squared theta, which is the law of Malus. Now, how do you calculate this? 1/2 of all of the light that gets through then? Well, we get 1/2 of all the light gets through by just integrating over the circle. Actually, you integrate over half the circle because there's no difference in being polarized that direction and polarized that direction. So you integrate from 0 to pi, and you get that half of unpolarized light is allowed through a polarizer. So those are wave optics things. Those are things that can only occur if light is a wave. We will come back to light as a particle after relativity. So we're going to come back and view light as a particle and show that not everything we learned is a crock of hooey, but that light is more complicated than what we've learned so far. All right, so any questions before we break for the day? You will note that the reading quiz is not, I initially put it for today, not remembering I was going to do reviews. So the reading quiz is on Wednesday, and likewise the homework is due on Wednesday. All right, have a great Monday, and I'll see you in lab for the exam tomorrow